So, hi everybody. So let's now finish up the day by detoning into some classical stochastic thermodynamics, and just want to thanks the organizer to give me the opportunity to present this work. This is joint work with Massimiliano Esposito, and it's, it's a review paper on the archive. So if there are any feedbacks, we're happy to have them. So so it's also a work that is the result of a few years of work within the group of Massimiliano Esposito. So it would be very hard to thank all the people who contributed to that. So in order to start, let me just show you a sort of sketch of a picture with it when I try to put on a chart different thermodynamic theories that have been developed through the years. A chart where I have this kind of axis, where on the x-axis I have dissipation, which is sort of measure of how far from equilibrium we are. You see the zero here where I have equilibrium. And on the second axis where I have essentially how many degrees of freedom I have in my system. And so historically, like our understanding of thermodynamic systems started with equilibrium, thermodynamics of heat engines, which is well, better describe the theory of thermostatics, since we need to have system always at equilibrium and they go slowly through equilibrium states. The theoretical microscopic underpinning was the equilibrium statistical mechanics developed by the ensemble theory of Gibbs and then the kinetic theory of Boltzmann. And from then, people then started at the beginning of 20th century to talk about linear reversible thermodynamics. So processes like transport processes, hydrodynamic equations, and their thermodynamics. The corresponding microscopic description is the one of linear response theory. So when we displace a little bit an equilibrium system, and we look at this response, so this is, think about Kubo and Green-Kubo response formulas. And here is close to equilibrium in the sense that we need to deal with system where currents and fluxes are proportional to each other. And as we all know, stochastic thermodynamics was born as in a way to go beyond this kind of framework to consider system where fluctuations are important beyond the Gaussian level and where currents are not necessarily, I mean, there are no linear functional forces. What we would like to do now, and what has been done in the last few years, is to discuss from a stochastic thermodynamics perspective system where there exists many degrees of freedom. So what I want to discuss now is essentially a sort of thermodynamic limits, but for systems that stay outside of equilibrium. And to do that, let me just remind what we know for just two things about the usual thermodynamic limits in equilibrium stat mech, where we can rely on a Boltzmann weight, which is the equilibrium distribution of states, which is just given by this Boltzmann factor. With here at the exponential, you see the negative of free energy of a system divided by the thermal energy of the bath. Well, usually what we consider are systems that grow large. So we can identify a scale parameter that I call V in this presentation, that can be the volume of the system, number of particles, or whatever. And in this limit, where V goes to infinity, well, we can identify intensive variables. We can have free energy densities such that the free energy becomes extensive. So we have that this capital phi can be written as V times the small phi. And everything about the macroscopic limit is then encoded in these free energy densities. This we learned in school or university, for example, in the prototypical model of Ising spins fully coupled to each other, which is the so-called Curie-Weiss model, where there is these spins that are coupled to from a bath at inverse temperature beta, and that's subject to an external magnetic field H. And of course, we know that as we lower the temperature, we go from a free energy density with a minimum, just a minimum, global minimum, to a free energy density with a flat part, which is a critical point, and then a free energy that develops two, if you want, fixed point, to minima that can be tilted by the addition of external field. So we have an understanding of phase transitions, both continuous, so the appearance of critical points, and discontinuous or first order. In terms of bifurcations, you see here the emergence, for example, of the two minima in this small plot, or in the sense of change of dominance between between minima of a free energy. And this is what we would like to understand or to have also outside of equilibrium. So to do that, let me just show you the kind of setup in which we can develop that. So it's the stochastic thermodynamics written in terms of systems that are discrete. So we can identify a configuration in terms of an occupation number vector for a site I. So this n is the occupation number. And the dynamics is given by a master equation where the capital R of rho are transition rates between the states on my system due to transition of type rho. And if all baths at equilibrium and the internal degrees of freedom of this mesoscopic state, occupation number, and are also at equilibrium, there is an ensuing local detail balance. That is to say, the log ratio of transition rates between nearby states. So states are at a distance delta rho, given a transition rho. So this log ratio is given by a difference of a state function, this capital phi, which we can think about as a free energy, but also another part that is not expressed, we cannot express just as a difference of state function, and is due to the non-conservative work produced by the coupling with external reservoirs. So this phi, you can think of it in the simplest case of a single thermal bath at temperature T, is really the free energy of the system, so energy minus temperature times the internal entropy, divided by the thermal energy of this thermal bath. But this can be generalized to other conditions. So in order to implement on these dynamics the kind of thermodynamic limit that I was telling you, we have to make some assumptions. So we have first to identify a scale parameter that I'm keeping calling V that goes to infinity. We have to identify or introduce some intensive variable like the intensive magnetization before for the Ising model, which I called C. So we scale the occupation number by the scale parameter. And we also have to take into account that as I have many more degrees of freedom interacting, I will have an increased number of transition per unit of time. So transition rates will become extensive. So I can introduce a macroscopic transition rate, which is this mole R of rho here. And the same extensivity happens for the thermodynamic quantities. So the free energy for system with short-range interactions, and you know what I'm referring to, we have that the free energy must be an extensive function that scales then with the scale parameter. While the part that comes from the conservative work of the external baths has to remain intensive because it's already expressed at the microscopic level as a difference of intensive thermodynamic quantities of the reservoirs. So as a result of that, I'm not going to give you all the details, of course, but just to tell you that, of course, as a result of the dynamics, the entropy production rate as well will be an extensive quantity. So it's useful to introduce an entropy density or an entropy production rate density, which is this small sigma dot here. What kind of system can we describe here? Well, I started with the analogy of equilibrium where we have the Ising model. Of course, we can generalize that model to a model with many states like the Potts model, and we can put forcing on that. We can put non-equilibrium driving, we can put a coupling to baths at different temperatures. And so these are all systems that can be described within these theories. There are also systems that are less, let's say, abstract, but that are very important for the point of view of applications. So chemical reaction networks, where we have different species, and this N, it's the number of particles that I have in my system. As the system grows large, I will have many more particles interacting and reacting. Also, electronic circuits can be described like that, and the number N here would be like the number of electrons that I have on each conductive element in my circuits. That grows large as the system grows in size. Okay? So the idea is that if you implement this kind of dynamics, what you have is concentration of probability. So probabilities become picked around the macroscopic states. So imagine that we have this pictorial representation here. What I'm telling you in maths is that the probability of a certain state in the large deviation language can be written as the exponential of minus v, my large scale parameter, times a rate function. And the macroscopic state is the minimum, is sitting on the minimum of this rate function. And if this rate function evolves and relaxes to a steady state, I will see that my macroscopic state follows this minimum and will eventually sit on the minima of this steady state rate function, which is essentially a non-equilibrium counterpart, a non-equilibrium generalization of a free energy. So exactly this minimum here corresponds to the most likely state, not only the average state, but the most likely state that will be denoted by x. And in the very macroscopic limit, its dynamics will be purely deterministic. So the x dot, the rate with which this state changes, will be weighted sum of the macroscopic transition rates, each of which weighted by the jump size of that transition. And this defines the macroscopic drift field that drives the dynamics of my macroscopic state. So as I was telling you in maths, what we have is that this rate function, the stationary rate function, is a Lyapunov function, meaning that my macroscopic state always decreases. The dynamics goes down into this rate function. And that's why it's also called the quasi-potential, because it works a little bit as a free energy. And indeed, in the equilibrium limits, so whenever I go back to a detailed balance dynamics, so I switch off my non-conservative work, it precisely go back to the free energy of my system. So we can be much more precise about the type of dynamics we are describing, and we can derive, for example, this decomposition of the drift field into two parts. So a first part is what I would expect from an equilibrium system. So it's a gradient descent, now not in the free energy, but in the quasi-potential, with the matrix here, which is a sort of mobility matrix, a positive definite mobility matrix. The second part, which is always absent for detailed balance dynamics, is the velocity in probability space. Sorry. So it's the ratio between currents and probability whenever I go to the macroscopic limit. And very importantly, these two quantities, they are orthogonal. So this means that I can really think about the macroscopic non-equilibrium dynamics as a superposition of a gradient descent in this cartooned quasi-potential here, times a circulation on its level sets due to the probability velocity. And since I'm out of equilibrium, I can have not just the boring fixed points that are the attractors that I have at equilibrium, like the bottom of the free energy well, but I can also have time-dependent attractors like limit cycles, quasi-periodic states, and also chaotic state if this nonlinear drift field is nonlinear enough. And of course, if I go back to equilibrium, I go back to the statement of equilibrium thermodynamics, that I know that just free energy will just be minimized by the dynamics. If we go a little bit a step further, so beyond the pure mean field limits, we can take into account the macroscopic fluctuations, which is essentially moving from a law of large numbers to a central limit theorem. This is essentially, I don't want to go into the details, but I just want to tell you the main facts is that we can approximate the typical fluctuations with the linear Langevin equations, that is essentially at equilibrium is the Onsager macro theory around equilibrium. So if we linearly displace the system around equilibrium, we can retrieve statements that are well known, like the minimum entropy production. But most importantly, we have to be very careful about this approximation, because first of all, if you want to do that thermodynamics, we cannot rely on this Langevin equation, because the entropy production rates associated to this Langevin dynamics, so the one that I would extract from a Kullback-Leibler divergence of paths generated by this Langevin dynamics, well, it's very different from the macroscopic limit of the underlying entropy production. And for example, it is proportional to the velocity of my state. So this means that if I'm sitting on an attractor that is a fixed point, this Langevin dynamics would predict zero dissipation, which is clearly not true in general. And the point is that this kind of Langevin approximation, even though it captures Gaussian fluctuations, it disregards completely the housekeeping entropy production needed to maintain a dissipative state. Okay, and of course you cannot hope to describe large fluctuations just going to a nonlinear Langevin equation, because of course this is not the correct way to do that. Just let me mention something more about the thermodynamics, in particular dissipation. So one of the things that we can do in stochastic thermodynamics is to derive useful decomposition of the entropy production rate. One of these is the splitting into adiabatic or keeping and non-adiabatic, which is the excess entropy production of a certain dynamics. In the macroscopic limits, we can actually show the non-adiabatic or the excess entropy production is exactly given by the time derivative of the quasi-potential as we follow the dynamics, the macroscopic relaxation dynamics. And before it's really descending from thermodynamics. On the other hand, if you plug this expression into the expression for the entropy production rate, well, you immediately get that the bounds on the entropy that you can produce along a relaxation dynamics that we like to call as a sort of emergent second law, because it's a generalization, it's a strengthening of the second law. It tells you that whenever you descend or you move from one state to another, macroscopically, well, you generate entropy, you produce entropy, and this entropy generation is bounded by the negative of the free end or of the quasi-potential difference between these two states. This bound is very important because this delta quasi-potential is actually what gives you the probability of rare fluctuations. For example, imagine that I have a nonlinear system. So I have a multi-well quasi-potential. I have a potential with different minima, and so a multi-stable system at the macroscopic level or a metastable system at the stochastic level. I cannot, if I wait for long times, well, there will be a rare fluctuation that brings me out of a certain minimum of the quasi-potential and through a saddle to another minimum of this quasi-potential, okay? The rate with which that happens, well, from large deviation theory, we know that is exactly given by the exponential of the quasi-potential barrier that my system had to overcome in order to go from one minimum to the saddle. And because of what I showed you before in the previous slide, well, I showed you a bound for this delta I of SS. Well, because of that bound and another one that regards the rare fluctuations, so not the relaxation, but the instanton dynamics, those rare fluctuations that bring you out of this minimum, well, you can also bound this transition time or this transition rate in this way. So this is bounded by the entropy that is produced in or negative entropy that is produced in relaxing down from the saddle to a fixed point, or it's also upper bounded by the entropy that is produced when I have this rare fluctuation that brings me out of my fixed point. Okay, and of course I can also show that close to equilibrium. So in the linear response regime, these bounds become tight. And so I have a sort of maximum entropy production principle. So the states that have a longer, so a smaller escape time or a longer lifetime, they are those that are surrounded by the largest dissipative barriers. Okay. So I don't have time to just give you an example, which is practical, because with this theory, you can really describe things that matter also in practice. For example, like memories. For electronic memories, for example, this escape time, they determine the time for which I can have I can store a certain memory in my system. And you can really show for these particular models of CMOS transistors that this time really scales as the exponential of the dissipation when you are far from equilibrium. Finally, let me just mention that here you can also take some kind of limits. So you can say that some of these transitions become very small. So it's a sort of continuous limit. And what we find here is essentially we refine macroscopic fluctuation theory, or it's another way of saying nonlinear fluctuating hydrodynamics. So we can describe field theories, stochastic field theories, and do the thermodynamics of them. Also, when some of these transitions are not going to a continuous limits. So I can mix together diffusive dynamics with reactions, so describing reaction diffusion systems, for example, or also active matter theories. Okay, so let me conclude. I'm trying to just give you a very broad overview of all the results that we have in this review paper. And essentially, we have a way to, through stochastic thermodynamics and its macroscopic limit, to organize essentially our thermodynamic understanding of systems that are either at equilibrium or close to it or very far from it. And we also have new results that would help us to construct a thermodynamics of dissipative states. So imagine that we want to discuss now the long time dynamics of jumps between these attractors that are now dissipative. Well, we have ways to do that, since we have shown, and we have shown how to derive the transition rates, how to bound them, and also how to essentially formulate the thermodynamics, for example, the dissipation of these long time jump dynamics over these dissipative states. Just the most important thing is that whenever you consider these kind of dynamics, well, the dissipation is not just given by currents, transition between these states, but also due to the housekeeping entropy production. So to what you have to spend in order to sit in a certain macroscopic dissipative state. So with that, I just close, and I'm open to question, and I invite you also to read this review and give feedbacks if you have.